All right, so yeah, the first part is just what is the speed of the ball at the top of the trajectory? Be the exact same question. And that's relatively easy because at the top of the trajectory, it only has an x component of that velocity. So I'm really asking for what is Vx, or really V naught x. V naught x is equal to V naught times the cosine of the angle. That's going to be 12 times cosine of 60. Is equal to 6 meters per second. So that's the answer for the first one, just the x component of the velocity. And then the second one, for part B, I want to know the range. I want to know the distance to go from here to here. I know that x is equal to Vx times t. I already have the x component of the velocity, that's 6 meters per second. So now I need to find the time. So in order to find the time, first, I need to know what is the y component, the initial y component of the velocity. That's going to be V naught sine of theta. That's 12 sine of 60. That's equal to 10.4. I'll just say 10 meters per second. And then I'm going to treat the problem like a one-dimensional problem where I have an object that goes up and comes back down again. And I know that the velocity at the top of this in the y direction is 0. So I can say then that Vy is equal to V naught y plus Ayt. That's going to give me the time at the top of the trajectory. So if I do that, I get 0 equals 10 minus 10 times t top. So t top is equal to 1. But be careful, I don't want t top. I wanted the time here. And so that time is going to be 2 seconds. Yeah. Yeah, so t top has to be 1. Right. So now that I know the time, I can find x. X is equal to 6 meters per second times the total time, not the time at the top, but the total time, which is 2 seconds. So that's 12 meters. And that's the answer. The second part is a little more complicated because you first have to find the time, and then you find the x range. Well, you have to find the time, and you have to find the y component of the velocity. It'll be exactly that. You're going to see other projectile motion problems in the multiple choice, so if you know this really well, that'll transfer over into those problems as well. Now the other one was this problem. I start by drawing all my forces. I recommend that you do the same. I have my normal force here. I have a frictional force. I know that it's down the inclined plane because the object is sliding up the inclined plane. So the frictional force is opposite the direction of motion. I also have a weight vector, Fw, that's going down like that. But I'm going to draw its components. I'm not going to draw it like that. I'm going to go ahead and draw the components of it, which would be here, this is the y component, Fw sine of 60, and here, Fw cosine of 60. So whereas I had that vector that was here, I've replaced it with its x and its y components. So I'm going to get rid of that again. So now that I have all that, I can go and answer the questions. I'll give you part A and part C here, not part B. The first one's just what is the normal force? Since there's no acceleration in the y direction, there's no acceleration in this direction, I can say that the sum of the forces in the y direction equals 0, or Fn minus Fw sine 60 equals 0, or Fn is equal to Fw sine 60. That's equal to 50 sine of 60. I think that's what, 43 newtons. So that's my normal force. That's part A. Part B, it's a little more complicated. I want to find the acceleration. It's going up the inclined plane. I already told you that. So I do the sum of the forces in the x direction equals max. That would be F plus Fw cosine of 60 minus 120, excuse me, F plus Fw cosine 60 minus 120 is equal to m times ax. I need to find F, script F, the frictional force. That's going to be mu times the normal force. That's equal to 0.1. I've already found the normal force. That's 43. So that's 4.3. And now it's just plugging in the numbers. So I get 44.3 plus the weight is 50. That's 5, the mass times 10. Cosine of 60 minus 120 equals 5 times AX. And then you solve for AX, and you get AX, what was it, like minus 19 or something, I think? 18, something like that. 18, minus 18 meters per second squared. All right, so those are those first two free response. And then the other two free response, I'll move down from here, y'all. Oh, wait. The other two free responses are going to be from exam 4. That's the manometer problem and the angular momentum problem. Any questions about this while I'm here? Gonna move on? All right. Sorry if I go too fast, but if I am, you just tell me to slow down, and I will slow down. All right. You're gonna have one like number 2, except the only difference is they're gonna be different shapes that are coming together, but otherwise they'll be exactly the same. I'll have one object that's moving. It's going to combine with a stationary object, and then I want to tell you what is the final angular speed of the two objects moving together. So they'll be moving at the same rate. So first, what is the angular momentum of the disk? L is equal to I omega. I for a disk or a cylinder is 1/2 mr squared. That's 1/2 of the mass, which is 4 times 2 squared. 2 times 4, 8. So that's 8 times omega, which was 3. That's equal to 24 kilogram meter squared per second. That's the total angular momentum. And that total angular momentum remains constant. So in part B, I'm saying Li equals Lf. The initial angular momentum is just that 24. The final angular momentum is going to be the combined moments of inertia, I of the disk plus I of the bar times omega final. I know I of the disk. I need to find I of the bar. For a bar, it's 1/12 of m. That's 3. That's the mass of the bar. The length of that bar is 4 meters squared. 3 times 4 is 4. So I of the bar is equal to 4. I of the disk is equal to 8. So I get 24 equals 12 omega F, or omega F equals 2 radians per second. And that's the right answer. So exactly like that, except the shapes are going to be different. So make sure you look at the equation sheet, and then also just be aware on this exam, one of these shapes is going to be a sphere, and on the exam, the spheres come up, and I don't know that we had any spheres on this exam, so just be aware that for the spheres, some spheres are hollow and some spheres are solid. So be aware of that. Make sure that you read the problem carefully. I'll say in the problem if it's hollow or solid, but just be careful, be aware. All right, finally, this last part. Here, which one is bigger? The pressure of argon is bigger. I have a bigger pressure here than I have here because the level is lower, so argon. Because the level is lower on the argon side, or something to that effect. And then the pressure of the argon gas, I know that P is equal to P naught plus or minus rho GH. Because the pressure P is bigger than P naught, this must be positive. P naught, so students made several errors here. First, they would get the sign wrong, whether it's positive or negative. Some students put that it's negative. Other students got the density wrong. The density, or excuse me, got P naught wrong. P naught here is 1 atmosphere, which is 1 times 10 to the 5th pascals. It has to be in SI units. This is 1 atmosphere right here, and that's equivalent to 1 times 10 to the 5th. You'll have a similar pressure. Plus, they got the density wrong, is mercury. Density is 13,600 times G, which is 10. Or they got the height wrong. Look, 92 millimeters needs to be in meters. In order to convert that to meters, you take that decimal point and you move it over 1, 2, 3 spots. That's 0.092. Those heights are often measured in millimeters for a mercury manometer, so that's why it's in millimeters, but you do need to convert it into meters. 3 decimal places over to the left. Make sure you get that right, okay. And then I don't remember what this was, 100 and something thousand, I forget what the number was, but whatever that was, that's the answer. Okay, that's the free response. You want to look at the multiple choice. Y'all have any specific questions about the multiple choice, Bethany? With time? Oh, the time. Yeah, let's start with exam 1 if that's okay. And then I think that came up with exam 2 or 3 or 4. What about exam 1? We will do that one when we get to it, okay? What about exam 1? Any specific questions on exam 1? You're not going to see these triangle questions, by the way, just because I don't know. Y'all are bigger than that. We sort of moved past that. So you're not going to see these basic trig questions, but you'll definitely see sig figs and estimations and the standards. So you'll see all of these, especially when you see 2 questions. Actually, I think there's a question from every topic. Pick 10 questions from each exam. There's a question from every topic. Conversions with powers in them. Be careful when you're doing those conversions that you're squaring or cubing or whatever you need to do to each conversion factor as it is relevant. So maybe not all conversion factors need to be squared, so just be careful with your units as you do that. You're going to see kinematics? Yeah. 12 and 13. Okay, I was about to ask about number 12. So you push a toy car horizontally with an initial velocity of 5 meters per second. So V0 is equal to 5. It decelerates at a rate of 1 meter per second squared. So A is negative 1 meters per second squared. I know it's negative because it's slowing down and the velocity was positive. So the acceleration is opposite the velocity. How much distance does it cover before coming to rest? So I know that V final is equal to 0. And I want to know what is x. Well, I know that x is equal to V0 t plus 1/2 AT squared. See, I know A, I know V0, I don't know X, I don't know T either. So I need to do a little aside work to find T. I also know that V is equal to V0 plus AT. V is 0, V0 is 5, A is negative 1, so that means T is equal to 5 seconds. So now that I know T, I can find X. X is equal to V0, which is 5 times T, which is 5, minus plus 1/2 of negative 1 times T, which we said was 5 squared. That's 25 minus 12.5, or 13 meters. Okay, you will have some kinematics questions, and they will be similar to that, where you have to solve for one variable in order to solve for the variable that you want. There are those similar to those on every exam, so if you're having trouble with these, then I recommend that you go back and work some of those from past exams. I think that the other kinematics question on this exam was similar, where you had to, I think that's right, for number 11, that it was a 2-step problem. And that will be the kind of problem that you'll have, where you have to solve for one variable and plug it into the other equation to find the one that you actually want. Keep those kinematics equations in front of you. They're not on the equation sheet, by the way. You'll have the full equation sheet, but those equations won't be on there. However, if you can't remember them, they're just like the rotational equations. Just remember that you're replacing your theta with x, your omega with v, and your alpha with a. And then those equations are the same. Okay, not going to see that one. Can we skip it? Is that okay? All right. Other questions, exam 1? Yeah, okay. 16. You definitely are going to see qualitative graphs and quantitative graphs, like 15, 16, 17, 18. There are several questions like that. That's a very important topic to me. Did you say 16? Yeah, and 16, like where I give you some situation and you pick the graph that describes that situation. This truck is traveling to the left. That tells me something really important, that it's starting with a negative velocity. And then also it's slowing down. So these are x versus t graphs. The slope of these graphs give the velocity. So I'm looking for one that has a negative slope to start. That's not that one, not that one. Then I'm also looking for one, it slows down, comes to a stop. That means that I start with a big negative velocity, big negative slope. It comes to a stop, so it has a 0 slope. But then it turns around and starts going back in the opposite direction, which is what it's doing here. So that means that D is the right answer. Okay, I want to know that you can take those words and in your mind construct the graph that describes it. By the way, I could also say, what does the V versus T graph look like for that same situation? V versus T, well, it's starting with a big negative velocity. It goes to 0, and then it speeds up in the opposite direction. So that's how that graph would look, the V versus T graph. Okay. Likewise, you should be able to give a V versus T graph and tell me what the position versus time graph is, or vice versa, give a position versus time graph and tell me what the velocity versus time graph is. Yeah, that's a good one. So here, the value on the V versus T graph gives the slope on the position versus time graph. The slope of a position versus time graph is the velocity. So here I have a big positive velocity. It's big. So I should have a big positive slope. But this has a small positive slope. This has a big negative slope, small negative slope, big positive slope. So I'm pretty sure D is the right answer. But notice here that my velocity decreases. That means that my slope decreases. Big slope here, small slope here. So yeah, D is the right answer. Yeah, they would be the same. It's just instead of moving, up and down, you'd be moving left and right. Mm-hmm. Did you say 17 as well, Kaylee? Sure. Why not? All right. So be able to know what the slope and or the area means. The slope of a V versus T graph gives me the acceleration. The area of a V versus T graph gives me the distance. So here I want to know the distance that it travels in the 4 seconds. That's the full time duration from 0 to 4. You need to find the area of this triangle. I'll break it into a triangle and a rectangle here and here. Remember, the area of a triangle is 1/2 base times height. It's just the area of a rectangle divided by 2, right? A triangle is half of a rectangle, or half of a square, depending on what kind of triangle it is. This is not equilateral. So that would be, in this case, 1/2 of 2 times 5, which is equal to 5. Be careful here, if you counted the squares, that's not what you would have gotten. You would have had 1/2 of 2 times 10 if you were just counting the squares. Don't count the squares. Look at the numbers, 2 and 0, that's the base. 0 to 5, that's the height. Here I've got 2 times 2, which is equal to 4. And here I have 1/2 of the base, which is 2. And the height is going from 2 to 5, so 3. That's equal to 3. So 3 plus 4 plus 5, 7 plus 5 is 12. All right. You have quite a few questions, too, that have to do with, have these kinds of questions, both with the graph, the qualitative graph, and you have to tell me which of those statements are true or false, but also questions with multiple statements. I retained a good number of those in this exam. So as you're going, I know you don't like those questions. No, maybe you do like them. Do you? You don't like them. You don't like them. You don't like them either. Okay. Oh, okay. 1 out of 8 people likes them. One, Oh, no, 1 out of 8, doesn't like. Okay, I like them. Anyway, I want to point out here, because 2 and 3 of these statements were sort of the hardest statements to imagine conceptually. The acceleration at point A is negative. That is a true statement. In fact, if I think about this part of the graph, if I have a position versus time graph that looks like that, this is a position versus time graph y versus t that describes an object that's moving up and then back down again. And I know in this case that the acceleration is negative 10 meters per second squared always. The reason I know it's negative is because, look, I have a positive velocity that is slowing. That means I have a negative acceleration. Over here, I have a negative velocity that's increasing. That means I have a positive, an acceleration that's in the same direction as the velocity, which is negative. And I also have a negative velocity, negative acceleration right there. Even though it's stationary at that point, the acceleration is still negative. So here I have a negative acceleration. Down here in this part of the graph at points B and C, I have a positive acceleration. It's just the inverse. You just take that graph and you flip it upside down. And for the same reason, it's positive. So this one's correct, but this one is not correct. Okay? All right. Other particular questions, chapter 1. Exam 1. Exam 2? No? 1? Pretty sure this one's on there. I don't think I asked what the speed of the projectile was. I think that I asked a simpler question. Let's do it anyway. It's still good to do. So I have this, and I want to know what is the speed down here. The speed down here has 2 components. The x component is whatever the initial speed is. Like this initial speed is the same throughout. So this component is 30 meters per second. So I need to know what is the other component. The first step is to find the time. With a projectile like this, you say y, consider the y displacement, which is negative 125 meters, is equal to 1/2 at squared. That's ay. Notice I got rid of the v0yt term. It goes away because v0y is 0. So that's negative 125 is equal to negative 5t squared. So t is equal to 5 seconds. It takes 5 seconds to get from here down to here. And in that time, the velocity in the y direction is going to be v0y, which is 0, plus ayt, which is negative 50 meters per second. So now if I want to know the speed, I have this component and this component. It's the square root of 30 squared plus 50 squared, which is, I don't know what that is. Uh, 58.3. A is the right answer. Okay. Pretty sure that one's on there. Something similar to it. Might have asked the range like I did on number 2. I don't remember. Don't hold me to that. But there definitely is horizontal projectile motion on the exam. One of these 2. All right. Again, you'll probably see some more of these from this exam. Other particular questions, exam 2? Yeah, Abby? 15? Definitely going to see one of these vector problems like number 9. 15. Definitely going to see one like 15, okay? I like that problem. So I recommend that you just label all the forces and then go through and hopefully the equations will stand out. So this is accelerating down the inclined plane, and there is a frictional force. So it's accelerating down in that direction. That means the frictional force is in that direction. I know there's a normal force, and then I guess just the weight components. I'm going to go ahead and do the components of the weight. Remember, like we did on the free response, I'm just sort of skipping a little step here. So that I have FW sine of 60 Sine for the y component, don't forget, it's like complementary angle, that 30-degree angle. FW cosine of 60 here. And I know that some of the forces in the y direction is equal to 0, and some of the forces in the x direction is equal to MAX. In the y direction it's 0 because AY is equal to 0. So let's look at these. If Fn equals FW sine of 60, since these two are opposed to one another and the sum of the forces in the y is 0, that is correct. And then if Fk is equal to mu k times Fw sine 60. That's just to say that Fk is equal to mu times the normal force. So that is true. Just that Fw sine 60 is the normal force. And then Fw cosine 60 minus Fk is equal to MAX. That's true. That's just a restating of this equation where I do the sum of the forces. Yeah, that's right. Be careful here because notice that you might have thought the signs were wrong because it seems like this should be negative, but it's not negative. This should be positive. It's in the positive x direction, and this is in the negative x direction. Because of the way that the inclined plane is drawn, that's a positive value. And then Fk is equal to Fw cosine 60. No, that's not correct. So it's just 1, 2, and 3. So you'll have that question with an inclined plane. May or may not have friction. It might be flipped around so that the signs are different. May or may not be accelerating. There may or may not be one other force. If there is another force, it'll be along the axis. That is, that it'll either be in this direction or this direction. Kind of like with the free response where you had that 120 Newton force. And then, of course, there'll be different equations. One of these on every exam past 20 years. So, yeah. 14. Okay. Here, how does this block accelerate to the right? So this is a two-dimensional problem, like the inclined plane problem, but it's there's not an inclined plane. But the steps are the same. That the first thing you need to do is to resolve the force vectors into its components. I'm just going to go and do that here. That this is 20 sine of 30. Is 10. And then this is the x component, 20 cosine of 30. To 17 newtons. And then I have a weight that is 100 newtons. And then I have a frictional force, because I know it's moving to the right, a kinetic frictional force. Now, I need to know what, I have one other force. Sorry, I have the normal force that is pushing up here, the normal force. I need to know what that normal force is. In order to find the normal force, normally the normal force would be 100 newtons, but now I have this extra force that's sort of pulling up. So now I know that the normal force is actually 100 minus 10, which is 90 newtons. Let me show you what I did there, actually. I sort of skipped a step. The sum of the forces in the y direction is going to be Fn plus 10 minus 100 is equal to 0. So Fn minus 90 equals 0, or Fn equals 90. Or down here, I just said, normally my normal force would be equal to the weight, but because I'm pulling up on it, I know that my normal force is less the weight by that amount, or 10 newtons. So that's why I wrote it that way that I did, but I got the same answer. So the normal force is 90 newtons. That means that the frictional force is 0.1 times 90, or 9 newtons. So this is equal to 9 newtons. And then if I want to know its acceleration, I say the sum of the forces in the x direction is 17. 17 minus 9 is equal to MAX. AX is equal to, what's 17 minus 9? 8 divided by the mass, which is 10, or 0.8 meters per second squared. Whew. It's a difficult problem. There are several steps that you have to do. But it's a lot like the inclined plane problem. I know it looks different, but the steps are the same. Resolve the forces, apply Newton's second law, and solve for whatever it is that you're solving for. Okay? Again, if not following, let me know. I can revisit it. Other questions from, was this exam 2, I think? All right. Exam 3. This is work, energy, rotation. 5 a.m. Have a good day, okay? True for y'all. If y'all need to go, I understand. This isn't helpful, you can go. You'll still get credit for it. Particular questions on this one? It's probably the easiest exam we had, huh? Was it exam 3? Is that true, or is that just me? I think that's true. Energy, work energy theorem, momentum, conservation momentum, impulse, that's that F equals delta P over delta T, and then rotation. Even though there are 3 chapters on this test, you still only get 10 questions from it on the final. They were 3 small chapters. Yeah. Sure. Yeah, you'll have something similar to this. So between midnight and 3 a.m., the hour hand has what displacement? Between midnight, the hour hand is right here, and 3 a.m., it's right there. That means it's going in that direction. So it's clockwise, so it's going to be negative. It's going to have a negative displacement. And then that's 90 degrees. So you have to convert that 90 degrees to radians. 90 degrees, there are 360 degrees and 2 pi radians. That's 90 over 3, that's 4, 2 over 4, pi over 2. So it's negative pi over 2. Or just know that 90 degrees is pi over 2. But make sure that you get the sign correct too. Notice there are 2 pi's over 2. 2 pi over 2's? 2 pi over 2's, I think. And so make sure you get the right sign. It's negative because it's clockwise. Okay, 5? Okay, so this is a work energy theorem. We said that work is equal to a change in kinetic energy. The way I usually think about these, though, is I think about this thing has some kinetic. Oh, wait, no, I'm sorry. This thing has a force that's being applied to it, and I want to know how much has its energy increased. The work that's done by that force is equal to F times D. It has, I'm sorry, never mind. There are two forces that are adding energy to this. The work done by the one force, which is 12 newtons, acts over 3 meters. That's equal to 36 joules. 36 joules. The work done by the frictional force is going to be negative 4 newtons times 3 meters, which is negative 12 joules. To find the total energy, you add those up, which is 24 joules. So the answer is A. So the question is, why is that thing negative? Well, if you think about this object, there's a 12 Newton force in this direction and a 4 Newton force in this direction, but my displacement is to the right. It's in the direction of that 12 Newton force. And I don't say that it's to the right, but it's in the same direction as the 12 Newton force. I could have drawn it the other way. So that's why the work done by the 4 Newton force is negative. It takes away energy. That's always true for us anyway, that friction will always be a dissipative force. It'll always take away energy. No, that doesn't matter. That just means that it's moving. Yeah, that it's moving. All right, other exams 3? Yeah, is that this exam? Okay. Let's do that. So we move on to exam 4, is that okay? And Bethany, you had asked about the MACE problem too, right? All right, can we do that one first since it's right here? All right, so here, this was a total energy, which means that I need the translational energy plus the rotational energy. There are 2 of those. That's 1/2. Oh, actually, never mind. I'm sorry. No. Because I'm throwing this thing up in the air. I want to know the potential energy plus the rotational energy. Guys, has this thing, he throws it up in the air, and then it's here, and then it comes back down again. So that's potential energy, which is mgh, plus rotational energy, which is 1/2 I omega squared. So the mass is 3 kilograms. G is 10. It goes to a height of 5 meters plus 1/2 of I. I is equal to 1/12 mb squared. It's 2 meters long and 3 kilograms. 1/12 of 3 times 2 squared. That's 3 times 4, 1/12. That's 1. It's convenient. So 1. And then omega is 4 radians per second squared. So that gives me 30 times 5 is 150 plus 1/2 of 16 is 8. 158 are 160 joules. Keeping proper sig figs. I do keep, some students ask me, I count off for sig figs. No, I'm not going to count off for sig figs, but I do keep proper sig figs in the answer. So be careful as you round and knows how to round that. And then a torque problem. I don't know, was there a torque problem outside of the free response? I mean, there was this arm problem. Let's look at this. This was a fairly basic torque problem, but applied for the human arm. The insertion point, that's where your bicep is attached, and it applies a force right there. And I wanted to know what that force is. I have another force down here that has a magnitude of 50 newtons. This 50 newtons, we'll call this F1, is applied at R1 equal to 0.35. We'll call this F2 is applied at R2 equals 0.03. So, the moment arm for the insertion point of the bicep is pretty short. That means that the bicep has to exert a really big force in order to lift anything that's substantial, really anything. That's why your biceps get so big, because you need a big force there. Same for your shoulders. I'm going to set these two torques equal to one another. F2 times R2 has to equal to F1 times R1. So F2 is equal to F1 R1 over R2. That is 50 times 0.35 divided by 0.03, which is about 580. Okay, but I could have looked at it and said, look, this distance is about 10 times this distance, roughly 8 or 9 times that distance. And so this force has to be about 10 times this force, which it is. Other questions from exam? Yeah. Number 3. You're going to have one of these. And ranking the torques, too. All right. No, we like ranking problems. Okay, so the key here is that you want the biggest moment of inertia is the one that has the most mass the furthest from the axis of rotation. So that's pretty clearly here D, because I got all this mass hanging out really far away from the axis of rotation. So D has the biggest moment of inertia. So that gets rid of some answers for me. I can get rid of A and D. And C has pretty clearly, I think, the smallest moment of inertia, because now I have mass that's relatively short distances from the axis of rotation. Remember, moment of inertia, we defined it as mr squared. So when I have mass at a big radius, because r is squared, then that mass more greatly contributes to the moment of inertia. The moment of inertia is dependent upon r. When r is big, the moment of inertia is really big. Okay, so C is the smallest. That doesn't help me because it's listed as smallest in those two. So now I need to differentiate between B and A. And a good way to think about it is, which has the bigger distance, from here down to here, or from here to here? Now they look similar, but we know that which of those is bigger? The hypotenuse, right. So that means that the moment of inertia about point B is going to be bigger than the moment of inertia about point A. So B is the right answer. I wouldn't say it was tricky, but it's not obvious just looking at it. You got to understand that's a right triangle and that distance is bigger. The one I give you is a little bit simpler than that, but you will still have 4 points on it, and a couple of those will be slightly ambiguous. You'll have to think about the distances. Okay? Yeah, Kaylee? Sure. Okay, so I have this potter's wheel. Potter's wheel is a disc, right? You don't know what a potter's wheel is, right? Listen, if I give you some object on the thing and you don't really know what it's like, there's no shame in asking me what it's like, what it is. What kind of object is this? I'll tell you, roughly describe the object, its physical dimensions. So a potter's wheel is a disc, and it's spinning at 3 revolutions per second. That's omega. It has a moment of inertia of 0.1. That's I. Bye, Abby. And a radius of 0.5. The potter throws a 1 kilogram lump of clay on the edge of the wheel. What is the new speed of the wheel? So initially, this thing had angular momentum. That was I times omega, 0.1 times 3, or 3. The units aren't right there, but that doesn't matter. Then the moment of inertia changes because this disk that had a moment of inertia of 0.1, you throw this lump of clay on the edge of it. Here's your disk. It's rotating about that point. And then you throw this lump of clay at a distance that's equal to the radius, 0.5 meters. So the question is, how do I deal with this lump of clay? Well, this lump of clay is considered a particle. And I just consider it a particle. A great way to tell if you discern whether an object is on that table or whether it's just a particle is to ask yourself, where is the axis of rotation? If the axis of rotation is inside of the body, then you're going to treat it like one of those shapes on the table. Or if it's a particle, if it has no radius, then it has no moment of inertia at all. If it's outside of the body, like it is here, that's a particle. Okay, plus I don't give you any dimensions of the clay or anything like that, so it has to be a particle. So I here is equal to mr squared, and for that lump of clay, that's going to be 1 times 0.5 squared, or 1/4. So I say that Li is equal to Lf. 0.1 times 3 is equal to 0.1 plus 0.25 times omega final. And then I solve that for omega final. That's 0.3 divided by 0.35 equals omega final. Should be pretty close to 1. Yeah, 0.9. Okay. Other questions on this exam, y'all? Or just in general, anything? Sure. Life? No questions about life? Okay. 10 from each exam. Yeah. So every topic is covered. I think it's pretty heavy on those statements questions, like I said. I like the ranking questions. There's a good mix of conceptual and calculations. I tried not to get rid of all the easy questions. I know some questions are harder than others, so I tried to keep a good mix of those. Was that a sigh? That sounded like a sigh. Okay, that all, y'all? Okay.